All right, so far with chapter 20, we've covered oxygen and nitrogen nucleophiles as they add into ketones and aldehydes. Now we're going to switch gears into more exotic ones, and we'll start off with sulfur nucleophiles. So I'll show you some simple reactions. In this example, we're going to start off with a ketone and 2 equivalents of a thiol. And under acidic conditions, you can end up attaching both of those thiols, just like with alcohols, to the ketone and kick off water. If you remember, the product, if you have alcohols adding in, is called a ketal or an acetal. In this case, this would be a thioketal, because it's no longer an oxygen, it's a sulfur attacking in. These honestly aren't that popular, they're not that useful, but I will show you the variation that is useful. And that's where you have a ketone like this. And just like with the oxygen analog, you can end up forming a cyclic thioketal. It looks like that, and kick off water. Does that make sense? So it's completely analogous. We're actually not going to cover the full mechanism for this because it is exactly the same as with oxygen nucleophiles. The neat thing with the cyclic version is you can treat this with a very special reagent called Raney nickel. Oops. And when you do that, you can actually pop off the sulfur groups and exchange them for hydrogens. And this mechanism isn't even covered in our textbook. It's fairly complicated. That should be a R-A-N-E-Y. And what Raney nickel is it's a nickel aluminum alloy. So let's make some notes. Raney nickel is a spongy nickel aluminum alloy with hydrogen absorbed. And like I said, you don't need to know the mechanism. This is a fairly popular reaction for a few different reasons. The first is it's relatively green. You don't have to worry about really strong acids or really strong bases. But what do you think a big downside to this reaction is from a practical point of view? Yeah, it's not the cheapest to run. What else? Super stinky. Sulfur-containing compounds will clean out a room. It smells really bad. So what I wanted to do is do a compare and contrast with similar reactions. So the first one we saw where we could get rid of a double bond to a carbonyl was the Clemmensen reduction. Oh, my goodness. And the Clemmensen reduction, if you remember, was for aryl containing ketones or aldehydes. So it's good for aryl ketones. So actually I'm going to color code this. And then the second one that we saw was the Wolff-Kishner. Reduction, and that was where we made our hydrazine, or we reacted a ketone or aldehyde with hydrazine. We made a hydrazone, and then we were able to blow that off as nitrogen gas, and we said that that one's green. So it works well in that regard, and it works with all ketones. And aldehydes, which the Clemmensen reduction doesn't work well with all ketones and aldehydes. And then I'm going to put rainy nickel over here. Like I said, rainy nickel also works with all ketones and aldehydes. And it is relatively green. However, now we need to cover the more negative aspects of each of these. Like I said, the Clemmensen reduction is not the best because it has mercury. It doesn't work well for alkyl ketones. Or aldehydes. And it won't work if you have acid-sensitive functional groups. I'll just abbreviate functional groups as FG. So the Clemmensen reduction isn't super popular anymore because of that. The Wolff-Kishner reduction, does anybody remember the one downside for the Wolff-Kishner reduction? What was that? It uses rocket fuel. That's one big downside. And then it doesn't work well if you have a base-sensitive functional group. Because we have to use stoichiometric hydroxide. Rainy nickel is good for all functional groups. However, like I said, it's stinky. So it's one of those situations where you kind of pick your poison. None of these are perfect, but they each have their strengths and weaknesses. They all accomplish the same goal, though, of converting a carbonyl group to a CH2 group. Does that make sense? All right. So now we get to do a little bit of review. And this is with hydrogen nucleophiles. Hopefully you can help me out with this. Let's say I have an aldehyde. And my goal is to convert this aldehyde to a primary alcohol. What reagent do I need? NaBH4, so sodium borohydride would work. PCC, if you remember, that's an oxidant. We're trying to reduce this. We're trying to add hydrogens in. So normally people will use NaBH4. And in this case, it's one of the hydrogens here on the BH4 that will get donated in as that blue hydrogen, right? It's important to remember that it's a hydride, not a proton, so it's a hydrogen with a negative charge. In addition to that, you also typically run this in a protic solvent to facilitate protonation of the alcohol at the very end. What's another reagent that could be used that's a little bit more aggressive? LAH. So I'll just put a little note here. It can also use LAH. So that's a simple hydrogen nucleophile, just treated as H-. It's a pretty simple mechanism that we've already covered. All right, same thing with ketones, where you can convert a ketone to a secondary alcohol. And just like before, you're adding in one equivalent of a hydride. And just like before, you can do this with sodium borohydride. Oh, let me keep the color scheme. And typically some sort of alcohol solvent. I'll just choose methanol. And just like before, both of these can use LAH. All right, and then last but not least, just to be thorough, even though it's not covered in this chapter, what reagent do we need if we want to reduce an alcohol, or sorry, a carboxylic acid or an ester? LAH. And for both of these, they actually make the same product, regardless of whether or not you're starting with a carboxylic acid or an ester, as long as that R group on the left is the same. And the only difference with this one is there are 2 steps. And then step 2, you typically will quench with some sort of weak acid or water. Make sense? Just some review. All right. So we've gone through oxygen nucleophiles, nitrogen nucleophiles, sulfur nucleophiles, and hydrogen nucleophiles. The next one, again, will be a little bit of review, and we'll do carbon nucleophiles. And let's practice. Let's say I've got this ketone. And my goal is to add in a new carbon group to this ketone. And make a tertiary alcohol. What reagent would I need? Grignard reagent, absolutely. So with the Grignard reagent, again, it's important to separate it out into 2 steps. So in this case, we would have RMGX, where R is now that blue group we want to add in. The carbon in this case has a very strong partial negative charge. You can even draw it as a full negative. And then in step 2, you would treat this with weak acid or even water to protonate it. Make sure that you do feel comfortable drawing the full mechanism for Grignard reactions. In addition to this, there's a new one that we will see in this chapter, called a cyanohydrin. And we're not going to get into the full mechanism for this, but it's quite versatile. Or you can take a ketone, react this with potassium cyanide, and in fact, let's draw out potassium cyanide. Actually, I'm just going to keep it as non-circled. And in this first step, the carbon here has a negative charge, so it can attack in and kick up electrons onto that oxygen. And then next, what you would do is treat this with a weak acid source to protonate this. And this is your cyanohydrin. The reason this is so versatile is you can convert cyanohydrins to amines or carboxylic acids. We're not going to cover the mechanisms now. We'll actually cover it later on. But for example, if you treat this with LAH followed by water, you can convert that nitrile group to an amine, so you're just reducing it. Alternatively, if you treat it with acid and heat, you can convert it to a carboxylic acid. And we'll cover that mechanism in more detail when we get to the chapter on carboxylic acid derivatives. And there you go. So like I said, make sure you know how to get to at least the cyanohydrin. We'll cover those blue arrow mechanisms later on. Make sense? All right, now we get to do the interesting reaction, the one that's very different. Arguably, the most interesting reaction from this chapter is called the Wittig reaction. And I'll show you the overall mechanism. And you can use either an aldehyde or a ketone. For my example, I'm just going to start with the ketone. But let's make a note it works with either. And with this reaction, you're going to react it with a reagent called an ylide. Does anybody remember what pH stands for? A phenyl group, right? So I'm just going to abbreviate that to avoid having 3 phenyl groups. And I'm going to attach this R group on here as blue. This phosphorus is typically represented with a positive charge, where this carbon's represented with a negative charge. And like I said, this is referred to as an ylide. And in this case, you can see the carbon here, because it has that negative charge, is a really, really strong nucleophile. And so it will want to attack the carbonyl carbon. And when all is said and done, what's going to happen is you're going to replace your oxygen with a carbon. And then that carbon typically has some sort of R group on it that will dangle off. So you end up making an alkene. And it's normally a Z alkene. Not an E alkene. So it's a really unique reaction where we're able to add carbons quickly and easily. You don't have to worry about all the problems associated with Grignard reagents, and it allows you to skip a few steps that you otherwise would have had to have taken to make the same alkene. So let's take a look at the overall mechanism. And we'll start with preparation of our ylide. All right, so the first thing you want to do is get triphenylphosphine. And again, pH just stands for phenyl. And then in the next step, you want to have some sort of alkyl halide, or at least something with a good leaving group. So I'll just abbreviate that as X. And I'm going to abbreviate the R group still as that red R. And in this reaction, you're actually going to do an SN2 substitution, where this lone pair on phosphorus attacks the carbon and kicks off the halogen. It's important to remember that because this is SN2, that this must be methyl or primary alkyl halide. If it's secondary or tertiary, it's just too bulky. The SN2 reaction won't occur, especially with a very bulky nucleophile like the triphenylphosphine. Okay, so let's draw the product of this. And we kicked off our leaving group, so I'll just draw that as X minus floating around over here. And in addition to that, our phosphorus has a positive charge since we've created a new bond. Okay, the next step, we're not quite at our ylide yet because our carbon doesn't have a negative charge, so we need to deprotonate one of those protons coming off of the carbon. And CH bonds, if you remember, are not acidic at all. They're one of the least acidic bonds in chemistry, so we need to use a really strong base. And the most common base that's used is N-butyl lithium. And the N-butyl just means straight chain butyl, so it's 4 carbons long, and the terminal carbon on the far side has a negative charge. Most chemists don't like writing this all out because it takes up too much time and space, so they just refer to this as butyl or butyl lithium. And it's a very, very strong base because that carbon is unhappy with the negative charge. So really quickly what it'll do is steal this proton. Now that carbon has a negative charge. Whoops, let me keep the R blue. And this is unique too because you can draw this in two forms. Where the one form has a double bond in between the phosphorus and carbon, and the other one is a single bond. Phosphorus is unique that way where it doesn't have to follow the octet rule because it's lower down on the periodic table. These each have their own unique names. The one on the left is called a phosphorane. While the one on the right is called the ylid. Typically when I draw it out, I draw the ylid form because it makes the most sense to have the carbon with the negative charge. But you may see on the ACS exam or in the textbook or just in other chemistry classes it's shown as a double bond form. They're equivalent reactivities. All right, so now we've got our ylid, that's the most important reagent. And we're going to see how this interacts with the ketone. So let's take a look at the overall mechanism. And this is one of the more unusual mechanisms you'll see in organic chemistry, so bear with me. So I'm going to flip my ylid around. So that the carbon is facing the carbonyl. And at this point, the carbon has a negative charge. Like I said, it's going to be very attracted to that carbonyl. And it's going to kick up electrons to that oxygen. Now at this point, the oxygen over here with the negative charge is really attracted to that phosphorus because it's got the opposite charge, right? So this will actually dump its electron density into the phosphorus atom that's next door. And you end up making this four-membered ring intermediate. Clean this up. Where this R group is still hanging off there. And each of these intermediates has their own goofy name. The first one that we created was called a beta-ene. And then the bottom one, which is arguably more important, is called an oxaphosphatane. It's a mouthful. And I'm hoping I spelled that correctly. All right, and then the last step, our goal is to form the double bond. And in order to accomplish that, what we're going to do is pop one of these sigma bonds over, and then the other one like that. So you're going to do a cyclic ring opening reaction. When you do this, you end up forming two products. I'm going to draw them both out. Mainly the ring strain. Yeah, the ring strain is not favorable. And then the second thing too is, I'll show you the products that are made. You see how we're getting a phosphorus oxygen double bond? This is called triphenylphosphine oxide. And this is commonly referred to as a thermodynamic sink. meaning if you form it, it's not going to go in the opposite direction. That actually helps push the reaction towards completion. It's similar when we talked about making nitrogen gas. Once you create nitrogen gas, it's not going to reverse anymore, and it actually helps drive the reaction progress. In inorganic chemistry, it's quite often to see triphenylphosphine oxide as a product simply because it's really, really stable. If you're producing it, it's going to drive the reaction progress forward. Okay, and then our second product that we actually care about is this one where we've now formed a double bond to a carbon. And like I said, this is normally a Z alkene. Does that make sense? So kind of a roundabout mechanism that involves that funky looking four-membered intermediate. All right, now we've got to practice this a bit more. So we're going to work backwards. So I'm going to give you an alkene, and I want you to figure out how to make this alkene using a Wittig reaction. So propose two ways to make this. So I'll give you a little bit of time to think about it, and then check with your neighbor and see if you agree on two different ways to make this. Raise your hand if you think you've got at least one way of making this. A few people. All right, let's try taking a look at this. What I like to do anytime I'm looking at a reaction where I might use a Wittig reagent is I just imagine working backwards and cutting that double bond into two pieces. So for example, I'd say, all right, this would be one blue half of the molecule, and then I'll pick this other one as the green half. So for example, I could say one way of making this would be to have the blue half act as the carbonyl group. Does that make sense? So I'm splitting it apart. That blue half, the double bond used to be to an oxygen rather than to another carbon. And then the corresponding piece must have had a carbon nucleophile. So we know this carbon must have had a negative charge on it, right? And then, in order to make this, it must be coupled to that phosphorus. It looks like this. So this would be our ylid reagent. Does that make sense? So one reasonable mechanism. All right, let's try another one. This time, I'm going to have the blue half be the Wittig reagent. Oops. So this time the carbon right here, actually I'll just keep it as a normal bond line notation. It's going to have a negative charge because that's the carbon we want to attack in, and then we must have this bonded to a phosphorus with a positive charge. And if that's our Wittig reagent, we must have some sort of carbonyl for the green half that looks like this, right? Do we agree on that? So two different ways. Now the million-dollar question, which way is better? So talk with your neighbor and see if you can rationalize which one's better than the other. All right, give me a thumbs up if you think you've rationalized which reaction is better, A or B. Give me a sideways thumb if you're just guessing at this point. That's a fair answer. All right, let's go way, way back to first term and think about nucleophiles. What makes a good nucleophile? We know it's something that's unstable, and then what's the second part? We want something that's not bulky, right? So if we think about bulkiness, which one of these is going to be less bulky and therefore be the better nucleophile? The reaction in B or A? B, absolutely. So one reason is that this is less bulky, better nucleophile. makes sense. The other really practical part of this is when we tried to make the ylid in B, or a Wittig reagent in B, it would go through a primary alkyl halide, which we know is best case scenario for making a Wittig reagent. For the reaction in A, we would have to go through a secondary alkyl halide, which we know isn't as favorable. So less bulky, better nucleophile is one part, and then can be made with primary alkyl halide. That means that this mechanism is the better mechanism. Does that make sense? So quite often when you're doing these, you have to consider both ways and ask yourself which one's better. The whole goal is to make the least bulky nucleophile so that it has the best attempt at attacking it. All right, let's do another harder one. This one might take more time. You got it now? That's good. Let's make this alkene, and you can only use cyclohexane and alcohols with 4 carbons or fewer. Oh. It's worth 4 points. Actually, I think this one's like a 7-point problem on exams. It's a synthesis problem. Little 7 down here. There we go. All right, let's try to do this as a class just because I'm worried we might run out of time. All right, so if we're working backwards, like I said before, I like to imagine cutting that double bond in half. And then we would say, all right, which side would be the better side to have your ylid be made out of, the green side or the blue side? Yeah, the carbon nucleophile. Should it be the green side or blue side? Green side, right? Because it's less bulky. Make sense? Okay, so I'm just going to erase this and say that means we're going to split this into 2 pieces. One piece would be the left-hand side, where there is a carbonyl right there. Makes sense? And then the other side, we know, must have had a carbon, actually 2 carbons. So I'm just going to draw out both carbons so we can keep track of them. Oop. PH3. The phosphorus is positive. This carbon must therefore be negative, right? So it's always the adjacent carbon that's going to be negative. All right, so we've got our Wittig reaction taken care of. Now what we need to do is figure out how we're going to make this component. So we can make this starting with our oh man, I'm forgetting what the name of it is. Our neutral starting material where we still have an extra proton on there, so let's draw it out. I'm completely blanking right now. Don't worry about it. You know, we all have off days. And then we needed what base? Butyl lithium, so I'll just say buly. All right, and then we'd say, all right, how do we make this? Got to do an SN2 reaction, right? So we must have had some sort of leaving group plus our triphenylphosphine. All right, so now we've made our Wittig reagent. However, we can't do that directly. We've got to start from an alcohol. So how can we make this from an alcohol? Substitution. Let's just pick a halogen. I'm quite fond of bromine. So how can we convert that alcohol to a bromine? PBr3. All right, so we've gotten all the way back to an alcohol. and we were able to convert that alcohol to a Wittig reagent and then couple it into our ketone. Now we've got to figure out how to make this ketone. So I'm going to work backwards this direction now. We know that we can oxidize an alcohol to a ketone using what reagent? PCC. And then we know we can make this alcohol a few different ways, but I'm just going to pick one. I can make it from an alkene. How? This is going way back. Chapter 9. What was that? Not quite. In this case, is there a Markovnikov or anti-Markovnikov side? No. So I might as well pick the easy one. I'll just use water in excess with catalytic acid. It would be, but why bother with a fancy reagent if you can get away with water? So you're not wrong. So we've got that. All right. Now if we think about this, we can say, all right, how can we make this from cyclohexene? Or cyclohexane. We can't do it directly. But what we can do is do a few-step workaround where we can say, we know we can do an elimination reaction, and we know we can make this from cyclohexane. All right, so now let's try to fill in the reagents we need. All right, so this one down here, what reagent do we need to go from cyclohexane to an alkyl halide like that? Br2 and UV light. So that's back from last term. All right, now how do we do the elimination reaction once we get the bromine installed on here? All the way back to chapter 8 now. Probably want a good, strong, non-nucleophilic base. I'll pick whichever one you want. Maybe sodium hydride. Something like that would work well to do that E2 reaction. I will say, typically these synthesis problems get more complicated as the year goes on, as you can clearly see. Try to practice these. Really review reactions from last term. And I will say on the exam, there's not one right way. At this point in the term, we've discovered many, many different routes to accomplish the same transformation. So if you are stuck and you can't figure out the Wittig reaction, see if you can find another reaction that works. I'm fine with that. All right, that's where we'll stop today. Tomorrow what we'll do is start up in the Baeyer-Villiger oxidation and finish up this chapter, and then do practice problems. On Wednesday, I want to see a show of hands. How many of you just want to do exam review versus how many of you want to do synthesis problems followed by an exam review? So let's see, exam review only. Synthesis problems followed by exam review? All right. So we may have our exam review after class. I'll record it for those of you that can't make it after class.